with IPv4, you want to perform route summarization. And there was two reasons why you really wanted to perform route summarization. Reason number one had to do with smaller routing tables. And you achieve smaller routing tables by taking a large number of routes, and instead of advertising them as individual routes, you advertise them as one route that represents them all. So you can take, for example, 16 routes, combine them all together, and just advertise one route that represents all 16 of them. It's nice to have smaller routing tables. But reason number two is that with route summarization, we now can stabilize our network. And we stabilize our network by controlling how far an issue will propagate in the network. And how is that accomplished? Well, when you're taking those 16 routes as an example and advertising them as one, if one of those routes, or 2 or 3 or 4 or 5, are going up and down, up and down, up and down, up and down, does that change the summary route that's being advertised? No, it doesn't. The summary route stays the same. That doesn't change. As long as there's one route that is part of the summary route that is still active, still alive, still available in the network, that summary route doesn't change. So now, if you have this part of your network and you are summarizing for all of those routes in that network out of an interface, well then anything that's flapping or anything that's changing over here is not going to change that summary route. Therefore, we don't have to propagate that changing, propagate that flapping throughout the network. So we stabilize the other portions of our network by not having, oh, this is up, that's down. Oh, this is up, that's down. Right? Stability is the key. Well, we want to do the same with IPv6, and you might be thinking right now, you're crazy. Look at the numbers. They're huge. How in the world am I going to take a 128-bit address, let alone 16 of them, or 64 of them, or 27 of them, and perform route summarization? Let me show you. It's not that hard. Do you remember earlier when we spent a little bit of time discussing shortcuts to route summarization? We can use those same shortcuts here. The ones for IPv4? Yeah, we can use them here. Let's take a look at this. Here you can see that we have contiguous IPv6 networks. So to take advantage of route summarization, you still have to design your IPv6 network properly. Set it up in a hierarchical structure so that way there you can do route summarization. If you have one network over here, and then the next network that would be contiguous is way over here, and then the next one's like over here, and then over there, and over there, then it's going to be very difficult for you to do route summarization and reap the benefits of it. So design your network appropriately so you can do route summarization in the EIGRP environment. So, are you going to convert the entire IPv6 address to binary? No, you're not. Not at all. Here's what we need to do. We just simply need to look at our prefixes in IPv6 and see where things start to change. I'm looking right now and I see that we have common values right up to this point here. Common values. Look at that. 2001, DB80. They're all the same. I don't have to touch those. Because what are we doing? We're looking for the portion of the address where values start to change. You're going to do route summarization to that point where everything is equal. So everything's equal up to this point. And then I see a 0, a 1, and a 2 in the fourth quartet. So let's break apart the fourth quartet now as they have done. And you can see it right here. It's broken up. There's 16 binary bits, 16 binary bits, 16 binary bits right there. So they only had to do 16 binary bits in this case. But what are we doing? We're looking for where things start to change. Let's find out where things start to change here. I see things starting to change right about there. Right there. That's where things start to change. Everything before that blue line is equal. Now all you have to do is figure out the new mask. Originally it was what? Originally it was 64. So now all you have to do is count the number of common bits. Well, that's a lot. That's a lot. So here's what I like to do. Subtraction instead. Take your original value of 64. Subtract from that however many you're going back by. There's our new prefix. And then all you have to do is grab the number that was listed first here. So 2001 DB8 00 62 summarizes all three of these. But it also summarizes 2001 DB 8 0 3 /64. So it does that as well. It would include that one as well, even though it's not a prefix that we are trying to include in the summary. But there's nothing we can do about that because that is how binary works. We're stuck at the mercy of binary. Let's discuss our shortcut method again. Do you remember what it was? What was step one? What was step one? Count the number of subnets. That's what it was. Let me repeat that. Count the number of subnets. 1, 2, 3. 3 subnets. 3 subnets. Step 2. Find the power of 2. Really? Powers of 2? Yeah, folks, we're still dealing with binary here, even though it's hexadecimal. We're dealing, the underlying values we're working with are binary. So, find the power of 2 that gives you 3. There is none. That's fine. There is none. But 2 to the power of 1 equals 2. 2 to the power of 2 equals 4. All right. So find the value that is closest to the number of subnets. So in this case, 3. That is over. Over. So it can't be under. You have to be over. So in this case, it's 4. 4. So 2 to the power of 2 equals 4. So what power of 2 gives you 4 now? And the answer to that is 2. The answer to that is 2. So we replaced 3 with 4. Because of binary, we can't do 3. It has to be 4. So now we have this value, this power of 2 to the power of 2. So this little number 2 that we see floating there is the number we subtract from the original prefix mask, which is /64. So we end up taking /64 minus 2 equals /62, which is right here. And then we take our original value, bring it down, and we get the same answer.